Hi, welcome to my channel, JaberTime. We're going to go over solving exponential and logarithmic equations. We're going to talk about the extraneous solutions. And the main thing that we're going to be using is if you have the same base, b to the power s equals b to the power t, we're going to take advantage of the common base and go directly to the exponent s equals t and move from there. One more thing is, if we don't have the same base, we're going to apply limit to both sides. Let's get started. Exponential and logarithmic equations. So this is the main theorem, or the main idea that we're going to be using. B to the power s equals b to the power t if and only if s equals t. Well, of course, if you have, like, let's say 7 to the power x equals 7 to the power 2, x has to be 2. It can't be something else. Here's a quick, simple example. The base is already common. It's base 2. 2 to the power x minus 1 is the same as 2 to the power 2x minus 4. Because of the theorem that we just talked about, we have a common base. We're going to just jump in and go directly to the exponents and have them equal to each other, because they have to be equal to each other. Imagine if you write 2 to the power 5 equals 2 to the power 7. That doesn't make any sense. So the exponents, because the base is the same, they have to be the same. Then after that, it's just like simple algebra to solve for x, and you should be fine. So we're using this one more time. Add 4 to both sides. Because it's simple math and algebra, I want to expose more examples to you. I'm writing the notes ahead of time instead of me as I'm recording writing. That's going to take longer. So a video that I make, if it's 20 minutes, and on the other side, if I write as I record, it's not going to be 20 minutes. It's going to be at least, I would say, 35 to 45 minutes. So hopefully that should help by having the notes ready and going over it. So we're going to add 4 to both sides. I get 2x equals x plus 3 minus 1 plus 4. Now we have x's on both sides. We want them on one side. So I'm going to subtract x from both sides. Because this is more, it's easier to subtract x and end up with positive x on one side. So that's the answer, and we should be fine. Let's take a different level question. When the bases are not fully ready for us, like it's so obvious here that we have the same base. In this case, this example, the bases are related, but they're not identical. But we could rewrite 8 and 16. We can write 8 and 16 as powers of 2. Then we will have the same base, which is 2. Here we go. We have 8 equals 2 to the third and 16 equals 2 to the fourth. We're going to go back in and use that for this problem. Take a look. Instead of 8, I'm going to write 2 to the third. We still have another exponent outside, which is x plus 2. Instead of 16, I'm going to write 2 to the power 4, still raised to the power x plus 1. But there is a formula that says we could multiply these exponents. And the formula is a to the power m to the power n is equal to a to the power m times n. This is what I just applied right here. Because we have the same base, we're going to go back and apply the same method. We're going to have the exponents equal to each other because the bases are the same. If these two quantities are identical and have the same base, the exponents, they have to be the same base. After that, it's just simple algebra one more time. Isolate x on one side and solve for it. I skipped the steps this time because I think we could manage and see more examples. So the answer is x equals 2. Let's take a different example. 2 to the power 5x equals square root of 2. Well, maybe it's not clear that we have the same base, but actually we do. And here's the reason why. It's 2 to the power half. And we have the same base. Instead of square root, I wrote half as an exponent. 5x will equal to half. Multiply both sides by 1/5. And the answer will be 1/10. Let's take a completely different example. 3 to the power x plus 1 equals -2. How do you solve for x where x is on top as an exponent, part of the exponent, and the bases are not the same or related? And for this one, you could apply ln to both sides, but if you could see it, you're done. This is what I mean. There's no solution. Why? Any power to a positive number like number 3 is going to end up positive. Imagine 3 to the power 1, 3 to the power 2, 3 to the power 3, 3 to the power even -2, which is 1 over 3 to the second. That's going to be a small number, but it's not going to end up negative. So there is no solution. There's another way to support it. 3 to the power x plus 1 is a graph exponentially increasing function shifted to the left 1 unit. Instead of going through 1 on the y-axis, it's going through -1, 1. So it's shifted to the left. This point, usually it's right here at 1. Since I don't have a number up front, the coefficient is 1. And this graph is exponentially increasing with the horizontal axis, the x-axis being the horizontal asymptote. But -2 as a different function is down below. They do not cross and they do not intersect. That is another way to see that this graph and this graph, they're not going to have anything in common, so there is no solution. Let's take a different example. 5 to the power x plus 2 equals 4 to the power x. As we could see, the bases are not identical and they're not close to each other or cannot be written with the same base. So what we're going to do, we're going to apply ln to both sides. Take ln of both sides, and by doing so, this exponent will go up front and this exponent x will go up front. Why is that? There's a formula in math that says ln x to the power a equals a ln x, or it doesn't have to be ln, natural log, it could be any log function. Log base b of m to the power n is the same as n log m with base b. So it's kind of like saying, short, take n, move it up front. And this is what I did. I took x up front, I took x plus 2 up front. Okay, then what? What could we do? See this right here, x plus 2 multiplied by ln 5. I'm going to do the distributive from the right side. I'm going to multiply ln 5 times x and ln 5 times 2. Here we go. Now, I could see this term has an x and this term has an x. This term is all numbers. So I'm going to move things around to have x's on one side. Okay, we use the distributive property here. We're going to move these two terms. This will go to the right. This will go to the left as a shortcut of saying it instead of adding or subtracting. But make sure that you change the signs. So now I have minus x ln 4. Instead of having it on the right, it's on the left. But take a look. I'm circling the x, which means what? I'm going to take it out as a common factor. We're going to factor out x. By doing so, I will have inside ln 5 minus ln 4. But I could simplify this even further. Here we go. Ln 5 minus ln 4 is ln 5 over 4 with 1 ln. Minus 2 ln 5 is actually ln 1 over 25. Why is that? First of all, the left-hand side, That's the formula. Then ln or log m minus log n with the same base. In our case, it's base e. Could be written as 1 log with a fraction of m over n. It's called the quotient rule for logs. This one right here, ln 1 over 25 came from minus 2 ln 5. And this is how. Minus 2 ln 5, I could take this back in. As you could see, I could take it back in right there. Then 5 to the power negative 2, I could write it as 1 over 5 to the second, which is 1 over 25. We're almost done. We just need x by itself. So I'm going to divide both sides by ln 5 over 4. Okay, here we go. Using a calculator, if you need the decimal form, it's approximate to minus 14.43. That's the x value. We're done. Here's a different form that we use solving log. Solving an equation of the form y equals a multiplied by e to the power kt. Exponential functions, as you could see. This is an example, which is 100 equals 20, e to the power 2t. I'm going to divide both sides by 20 to clean this side and have the exponential by itself. Now, since I have e to the power 2t by itself, I'm going to apply ln to both sides. Why is that? Because ln, or natural log, and the exponential function with base e are inverse of each other. They're going to cancel. That's one way to say it. Differently, you could think about e as a base e to the power what equals e to the 2t, which is 2t. So that's one way to say it. Or I could bring the 2t up front, and then will become 2t times ln e. But ln e is 1. Ln goes like this and goes through 1. Ln e is 1. So what we have here, ln 5 equals 2t. We will need t by itself, so I'm going to divide both sides by 2. And once I do that, I'm almost done. Cancel the 2. And t equals ln 5 over 2. Let's take another example. Pretty much almost the same, except I have one more term in the way, which is the 5. We need e to the 2x by itself. I need to get rid of the 5. I need to get rid of the 4. We are going backwards, so we get rid of the side number first. Addition first, the multiplication, because we're going backwards. It's not the same as order operations, but it's the other way around. Here we go. First, we subtract 5 from both sides. I get 4 e to the 2x equals 7. I'm going to divide now by 4. And I end up with e to the 2x equals 7 over 4. Well, I need to bring the 2x down to solve for x. To reach and bring it down, I'm going to apply ln to both sides. Pretty much for now, you could see the pattern. Same base, you know how to do it. You compare them. If not, you apply ln to both sides to bring any exponents down. We're going to bring this up front, and this is just a number. 2x up front, or this one you could just like think differently as e to the power what is e to the 2x, which is just 2x. So the left hand side becomes just 2x. 2x equals ln 7 over 4, divide by 2, divide by 2. And that's the answer. That's it. Here's another topic that we're going to have to deal with sometimes, and be careful, especially if the question says check for any extraneous solutions. Here we go. In different topics like squaring and using the square roots, this might happen because of the restricted domain. In this case, sometimes because we apply logs and we use exponentials, they do have restricted domain. In other words, log has a domain which is greater than 0. So if you have log of a negative number like -5, that's undefined. You could try it on your calculator. That's not going to give you an answer. So let's make it happen and read this quick and see some examples. Sometimes the methods used to solve an equation introduce an extraneous solutions, which is a solution that is correct algebraically. It looks like everything is correct in steps, but does not satisfy if you check the number back in the original equation. Does not satisfy the conditions of the original equation. One such situation arises in solving when the logarithm is taken on both sides of the equation. In such cases, if that's not happening, you have to check the restricted domain. I'll show you that in the coming example. In such cases, remember that the argument of the logarithm must be positive. Log 5 is defined, log negative 5 is not defined. That's what we mean as an example. If the number we are evaluating in a logarithmic function is negative, like negative 5, there is no output. Now, here's an example. Solving exponential functions in quadratic form. It's a completely different type, but at least you get the benefit of knowing how to solve with factoring, and we're going to check for extraneous solutions. We're going to think about this after I move the 56 to the left as it's a second degree equation. How is that? Well, if this is e to the x, I think e to the 2x is the same except e to the x to the second, which becomes e to the 2x. So I could factor it. E to the x times e to the x is e to the x to the second, and that's the same as e to the 2x. 56, 8 times 7. We need to have a negative. One of them has to have a negative because I have in the middle a negative sign. I'm going to give the negative sign to the bigger one to end up having a negative as a net. Well, to explain this right here one more time, I could show you here in detail what do I think. E to the 2x is e to the x to the second. So if you call e to the x u, that's called u substitution. E to the x to the second minus e to the x minus 56 will look to me as u to the second minus u minus 56. And if you're going to factor it, it's like u plus 7 times u minus 8. That is u plus 7 times u minus 8. Now this will give you two options. Either this equals 0 or this equals 0. Subtract 7 from both sides. Add 8 to both sides. I get the following. Now we're not going to take this because the exponential functions e to the x lives above the x-axis because it doesn't have any shifts right, left, up, or down. It's going to stay above the x-axis, so there is no way that's going to give me an output or be valued as negative 7. E to the x equals 8 could be solved. So the answer is e to the x equals 8. Or we need x by itself. So we're going to apply it to both sides one more time. Bring the x down. As you can see, I'm focused on this one. This one I'm not dealing with, and I'll show you that in just a minute. Apply it to both sides. Bring x up front. So x ln e, and ln e is 1. Or think about e to the power what equals e to the x. It's just x. Equals ln 8, and we're done. Now let's confirm why we're not taking this. We're going to reject e to the x equals 7, negative 7, since e to the x cannot be negative. And this right here could be, if you don't want to bring the x up front and call it ln 1 equals e, ln e equals 1, I'm sorry, you could read this differently as e to the power what equals e to the x. That should be x. So this whole thing on the left is just x. Alright, I think that should do it for this problem. And if you want to solve e to the x equals negative 7 to help support this and understand it, here we go. If you want to solve e to the x equals negative 7, which we said e to the x cannot equal to negative 7, which means we have to reject it and not consider it as part of the solutions. Here we go. Take len to both sides. Apply len to both sides. Len e to the x, that's an x. Len negative 7, well, len goes to the right only. Log functions, they have a domain that is x greater than 0. That is undefined. That's not real. You can try to the calculator will display a message to you that it's an error or it's not a real number. So we could solve this in different ways. End up with x anyway equals len negative 7, but you can't walk away and leave this as an answer. Len negative 7 is not a real number, and in the real number system, this solution is rejected as an extraneous solution. Okay, it looks like it's a solution, but we cannot accept it. Let's take another example. Using a graph to understand solutions, we had one before, but let's do one more. Len x equals 3. If you want to solve this, think about it. The base is e to the power 3 equals x. So we're done. E to the 3 equals x, or x equals e to the third. We're done. That's it. To support that graphically, we could consider this to be called y1. We could consider this to be called y2. And we graph y1, graph y2 on the same grid. This is y equals len x. As I said, the domain is x greater than 0. All the way up to 3, that's a horizontal line called y equals 3. Where they meet is our solution at x equals approximate 20.0855, which is e to the third. So the graphs of y1 and y2 cross the point e to the third and its output, which is 3, which is approximate to what I just said a second ago. That should do it, and I'll see you in the next one. Thank you.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.